A warm welcome to one and all. Here we are going to see about JFET circuits. I am J. Gurumurthy, Assistant Professor in Department of ECE in R.M.K College of Engineering and Technology. And FET transistors can be classified as depletion mode and enhancement mode. Again, we have two types of FET. One is JFET and MOSFET. JFET will come under depletion type, and the MOSFET will come under enhancement type or depletion type. So what is enhancement type? You have to apply a minimum potential at the gate terminal to create channel between source and drain, which is called as enhancement device. Enhancement in the sense you will have to give some external potential to the gate terminal to create channel between source and drain so that current conduction take place. In the case of junction field effect transistor, it is a depletion type. So it says that the channel will be present inside the device. You have to deplete the channel to control the current conduction inside the device. That is called as depletion type device. And if you take JFET, the construction itself, gate will have p-type material and source will have n-type material. Source and drain where the channel will be present. So source will be n-type and gate will be p-type. You will have to reverse bias the gate to source terminal. So if you reverse bias it, the impedance in the impedance of the device will be more and gate current will be ideally equal to 0. So if that is the case, if you consider this as the JFET, this is gate, this is drain, and this is source. So when you consider this, apply KCL, the current entering our gate current plus drain current is equal to source current. So we said that gate current is 0. Why? Because the device has been, the gate and source junction will be reverse bias. So it is ideally been equal to 0. So IT is approximately equal to IS. This is the first thing you should understand in JFET. And the second thing is, it is a the drain current depends upon IDSS, which is saturation current, drain saturation current, 1 minus VGS by VP. So if you take this graph, this region upon this point, the current in the drain current remain constant. So it is called saturation region. So below this, the drain current is going to change with respect to voltage. So it is nothing but linear region, or it could be called as triode region. So for normal FET amplification, the FET should be biased in saturation region, and the drain current in saturation is nothing but IDSS 1 minus VGS by VP the whole square, and the square says it has square law dependence, which makes the device non-linear, right? So when you design amplifiers, you will have to work with both DC signal and AC signal. So why DC? DC is required to bias the transistor to sit in saturation region, and AC is given at the input, and you will have magnified output at the output of the amplifier. So when you do DC analysis, the first step is capacitor should be considered as open circuit. Why? Because if you take reactance of the capacitor, it is 1 by 2 pi f into C. In DC, frequency will be 0. So f is 0. It says 1 by 0. So 1 by 0 is nothing but infinity. The infinity resistance or impedance is nothing but open circuit. So capacitor should be considered as open circuit. And the circuit, after considering capacitor as an open circuit, is called DC equivalent circuit. So what you will do with the DC analysis, you will fix the operating points, which is nothing but the IDQ and VDSQ. And those parameters are called as large signal parameter, because the quantities of voltage will be larger than AC signal. So that's why it is called large signal parameter. And then you will have to do AC analysis, where capacitor is considered to be short circuit. Why? Because again the same reason, XC is equal to 1 by 2 pi FC. When you increase the frequency, the reactance is going to decrease. So we are going to consider at frequencies, higher frequencies, the reactance of the capacitor is considered a short circuit, and the circuit, after considering capacitor as a short circuit, is considered to be AC equivalent circuit. and then the next step is replace the transistor by its model. What is a model? Model is a combination of circuit element properly chosen, the best approximate the actual behavior of the semiconductor device under certain operating conditions. So if you consider the model for saturation, this model can be used for when the device is operating in saturation. You can use this model. So we know id is equal to idss 1 minus vgs by Vp the whole square. We have seen in the previous slide. So differentiate this equation with respect to what is trans conductance Gm. Conductance is nothing but I by V. I is nothing but drain current and V is nothing but VGS. So differentiate ID equation with respect to VGS. We will end up with 2 times of IDSS divided by minus Vp into 1 minus VGS by Vp. And the other parameter is nothing but R0. R0 is channel length parameter, which is 1 by lambda id. So R0 is 1 by lambda id, right? And these two parameters are called small signal parameters. And why it is called small signal? Because with the applied input signal, AC signal will be much smaller, so that's why it is called as a small signal model. And then we will go into the problem. So determine small signal voltage gain of a JFET amplifier. So this is the amplifier where considering the details such as the transistor parameter IDS is equal to 12 milliampere and Vp is equal to minus 4 volts and lambda is equal to 0.08 volt inverse, and determine the small signal voltage gain. So first step is draw the DC equivalent circuit. So capacitor should be considered as open circuit. This is open circuit, this is open circuit, and this is open circuit. So this source, Vi source, will not have any effect on the amplifier. RL will not have any effect on the circuit. And this when it is considered as open circuit, RS will be present. So the circuit will not contain AC source. So you can call this capacitor as a blocking capacitor because it blocks DC into the source. And when you couple the output of this amplifier to the next stage, this avoids the DC from here to flow into the next stage, but it will allow only AC signal to flow. It will allow only AC signal to flow from this circuit. So this is the importance of using capacitor in the amplifier. So the first step is DC. We will have to draw DC equivalent circuit. RD, RS, R1, R2, and it is VDD, which is equal to 20 volts. So this circuit is called DC equivalent circuit. It contains only DC. So the DC analysis is meant for obtaining the Q points, which is IDQ and VDSQ. We will obtain that VGS, which is nothing but VG minus Vs, Vg, which is nothing but the voltage at the gate terminal, and it has been fixed by R1 and R2, which is nothing but voltage divider network. So R2 by R1 plus R2 into VDD, and the Vs is nothing but the voltage across Rs, which is Is into Rs. So we want VGS. I know R2 is equal to 180K and R1 is again 420K plus 180K into 20 minus Is would be nearly approximately equal to ID into Rs. And we know, so when I do the arithmetic, ID is nothing but IDSS 1 minus VGS by VP the whole square into RS, which is 2.7 K. So if I cancel this, so it is 3 into 2, 6 volts. IDSS is 12 milliampere. RS is 2.7 K. It is 1 minus VGS by VP is minus 4 the whole square. So VGS 6 minus 12 milli into 2.7 K, it will be it will be 32.4 into 1 plus VGS by 4 the whole square. So I expand this, 1 plus V square GS by 16 plus 2 times of VGS by 4. So this would be written as 32.4 1 minus 1 plus VGS square by 16 plus VGS by 2. So 6 minus 32.4 minus 32.4 V square GS by 16 minus 32.4 VGS by 2. So 6 minus 32.4, it is minus 24.4 minus 32.4 divided by 16. So it is 2.025 V square GS 16 point, so it is 16.2 VGS. So I could write this as minus 2.02 V square GS minus 17.2 VGS minus 24.4, which is equal to, so it's a quadratic equation. When I solve for VGS, I will end up with getting this, sorry, it is 26.4. We have made an arithmetic mistake. So VGS is equal to minus 2 volts. So this VGS is going to fix my IDs, because ID is IDSS 1 minus VGS by VP Q whole square. So this VGS minus 2 volts is going to fix my ID. So I could call this as VG SQ, and I could call IDQ as Q point drain current, which is IDSS 1 minus VGS by VP the whole square. Substitute the values, we will end up with getting IDQ, which is equal to 3 milliampere. And the next step is we'll have to get the GM value. So GM is equal to 2 times of IDSS by minus VP, 1 minus VGS by VP. So substitute the values, we will end up getting GM is equal to 3 milliamp per volt. The next step is you will have to find R naught. R naught is equal to 1 by lambda IDQ. So lambda is 0.008 into IDQ is 3 milliampere. So if you solve for this, you will end up getting 41.7 kilowatts, right? So GM 3 milliamp per volts, R naught is equal to GM 3 milliamp per volts and R naught is 41.7 kilowatts. Okay, we will have to draw AC equivalent circuit and replace the transistor by its model. So when you replace it, so while drawing AC equivalent circuit, this capacitor should be considered as short circuit, this capacitor is considered to be short circuit, and again this considered to be short circuit. So RS will not have any, the presence of RS will not be there in the AC equivalent circuit because RS in parallel with a shunt, so it will become zero resistance. So this RS will be absent. So when you draw the small signal equivalent, small signal or small AC equivalent circuit, you will have both R1 parallel R2 this case it is GM VGS, this is R0 and I should have RD and I should have RL and I will take the output here. So I want voltage gain, which is AV, which is nothing but V0 by V in. V0 is GM, VGS is the current which has been flowing. So this current is going to flow in this path. So minus GM VGS is the current and it has three resistors in parallel. So R0 parallel RD parallel RL divided by V in and So this is gate, this is source, and this is drain. So minus GM. So gate is being connected with VN. So VGS can be written as VN R0 parallel RD parallel RL by VN. I could cancel this. So minus GM is minus 3 milliampere. R0 is 41.7 K in parallel with RD is 2.7 K. Parallel with RL is 4 K. So all these parallel combination will end up with resistance value much smaller than the lower resistance, which is 2.7 K. So when you do the manipulation, you will get gain is minus 4.66. 4.66. So this is the gain of the amplifier, right? Thank you all. With this, the lecture is over. Thank you.